let's try to understand how the FM is generated, first of all, in time domain and what the FM signal looks like in the transform domain. So we have seen a simple basic FM transmitter system, and we have talked about how the instantaneous frequency is varied. Instantaneous frequency is a variable, of course, it's a function of time, and how it is being varied. The nominal frequency of the carrier is being varied with respect to the amplitude of the audio or the modulating signal. So this is a very simple setup that I've explained before. So for example, over here, whatever the signal you get from the microphone, let's call this as audio signal, and this audio signal is varying the frequency of the voltage control oscillator, who's as having a nominal frequency of omega naught, and this frequency is being varied with respect to the amplitude of the audio modulating signal, VAT. Okay, so let's try to see how we can generate this. These generations are in MATLAB. So what I did is I have a 25 hertz sinusoidal signal. So you can see that the frequency over here, one waveform is 0.04 seconds. Time is in seconds. So then this is the second wavelength. So you can see, you can infer from here the information that the modulating signal is a sinusoid having amplitude of +1, -1, and the wavelength is telling you that this is a 25 hertz signal. Now we consider a high frequency carrier signal, 400 hertz. Okay, you can see the waves are more bunched together. It's a high frequency signal. And I've considered an arbitrary modulation index of 10. What is modulation index? So if you recall over here in the previous discussion, this is your modulation index. Okay, so these excursion means deviations from omega c. So over here, you see this is your modulation index. How much you are deviating. For example, if this is a sinusoid, happens to be a sinusoid, then the amplitude of this sinusoidal phase term you see over here is k oscillator over omega a. That's your modulation index. Okay, so the maximum phase excursion is known as the modulation index, and that's the maximum phase excursion or deviation because this is a sinusoidal signal. So either it's +1 or -1. So let's keep this value as equal to 10. I've set this to 10, but then again it's a variable, so it depends on how much you change it, and depends on this modulation index, the frequency or the bandwidth requirement of the FM signal. So as we're going to look at this. So for this you see the modulation index is 10, and you see when the amplitude is when the amplitude starts decreasing, the instantaneous frequency is low over here. Okay, so it starts decreasing from 0.01. So you have more frequency. F is high in this region. Then the instantaneous frequency is decreasing in this region up until 0.03. Okay, so you have the waves that are not much closer to each other in this region. Then again, as the amplitude starts rising up until 0.5, you see the waves are more bunched together. Then again, the waves are relaxed. Okay, so it looks like a series of compression really function as a longitudinal wave, mechanical waves. Anyways, so you see with respect to the amplitude, the frequency is being varied. Okay, so over here again, let me put it like this: the omega c or fc is omega c or fc is again the nominal whatever the frequency of the carrier is as a function of time, and we are varying this with plus I have a modulation index. Let's call this M, modulation index MI. Okay, multiplied by VAT. Okay, so modulation index multiplied by VAT. That's how you're varying the frequency with respect to the, let's say, depending on the amplitude and the modulation index of the modulating signal. Now, if on the other hand, if the modulation index over here is small, okay, you see that the variation is hardly noticeable. It's hardly noticeable. You don't see much bunching of the waves together and relaxing simultaneously. So what is happening here is you see around DC, this is normalized frequency. Notice that this is normalized frequency. Normalization is with respect to this normalized frequency is basically this is equal to 2 pi f over fs, where fs is the sampling frequency. But anyways, for the sake of the plot, this is the scale is set to the normalized frequency variable. So it has no units. Okay, so normalized frequency multiplied by pi. So this is actually pi over here. This is the digital frequency. Anyways, so 25 hertz is close to DC. You can see a peak over here. So this peak corresponds to 25 hertz. This is a 25 hertz peak. Okay. So we have a strength. We have a single tone actually. We have the only frequency is 25 hertz. This is the wavelength. Okay. So this frequency is 25 hertz. So FM is 25. So this is 25 hertz, and this is what you are looking over here, right, at the spectrum. Similarly, for the carrier, you have a 400 hertz single tone, and this tone is, you see, it's at 400 hertz. It's not around DC. Okay. Again, this is normalized. If you denormalize, then this is 400. Okay. This value is 400 hertz. 400 hertz. So what happens is that the spectrum around 400 hertz, it's a very narrow peak. It looks like a very narrow band. It's similar to very narrow band. Looks like a narrow band AM. Okay. So this is a narrow band spectrum. This is a narrow band FM spectrum, or just similar to what you have in AM. So it's not much different. So once you have this small modulation index, you see the deviations are hardly noticeable. Modulation index is again the deviations. So if you're not deviating the nominal carrier frequency, you're not much deviating from that. The resultant spectrum of the FM is narrowband. Okay, it's narrowband. So let's vary this modulation index again to see its effect on the spectrum. Now this is 10 times of what we had previously. Okay, and you can see that the spectrum, it looks like it's again narrowband. I mean, it's this is the band of the frequency that is that's taken up by the FM signal. So again, it's narrowband. You keep on increasing the deviation. So as you increase on as you keep on increasing deviation, the resultant band increases. The spectrum of the FM signal becomes broadband. Why it's broadband? Because you require more frequencies. Okay. So for example, when the modulation index is 10, you see, as you've seen before, the excursions or the deviations you see in these regions, and this region, the deviation is more noticeable. And this results, for example, the frequency, or whatever the frequency is it's a variable, but it is dependent on the given amplitude. But if you make the modulation index small, if you make the modulation index very small, well, even if the amplitude is high, the deviations are hardly noticeable. Okay, you're not deviating anything. This modulation, if this is low, if this is 0, you're looking at the same carrier frequency. Okay, so the spectrum is very narrow at the same peak what you have earlier around the carrier frequency. That's what it is. Now, so if you increase that, of course, the excursion, the deviation in the frequencies are more noticeable. So more frequencies means you are having a broadband FM. So let's still increase this by a factor of 10 again. So this modulation index is 100, and you see there's more bunching of frequencies. The frequency is very high over here, very low over here, and from very high transitions to low transitions, high transitions, low, and this happens smoothly as a function of the amplitude, okay, amplitude of the audio signal. So you see the spectrum becomes even broadband. The spectrum has a very large bandwidth. Okay, spectrum has a very large bandwidth, and this bandwidth. So what we can deduce from these simulations as a variation of modulation index is that the bandwidth of the FM signal, is, I can easily say that bandwidth, it depends on the modulation index of the FM signal. Okay, so bandwidth of the FM signal is proportional to the modulation index. If the modulation index is high, the FM signal is broadband. If it is low, well, it's a narrowband FM. It's a narrowband FM. Okay. Now, as we have talked about the phase modulation scheme earlier, the phase modulation differs from the FM only in that it does not have this omega A in the denominator. Well, where was this omega in the denominator? We have seen this before. It occurs because of the integration, right? So what we did is we integrated this, and this omega A that came down over here in the denominator is due to the integration. Okay, so since we are in this is the frequency that has been made that is made as a function of time, and that is being varied. Since this is being varied, the frequency is being varied with respect to the modulating signal. In phase modulation, the phase is the phase has to be varied with respect to the modulating signal, okay, directly. So you don't need this integration operator, so you don't have omega a in the denominator for a PM signal. Okay, so that's the difference only primarily. So phase modulation differs from the FM only that it does not have a omega a denominator. It could be produced by a fixed frequency oscillator followed by a voltage controlled phase shifter. That's the direct method, that you have a voltage control oscillator. And for example, over here, what we were doing previously from the generation of FM, we have voltage control oscillator, and its voltage is being controlled by an audio signal. Okay, so you don't need that. What you need over here is a frequency shifter. Okay, sorry, the voltage control phase shifter, and that's it. So an indirect way to produce the PM from the FM, well, this is an indirect way. So if you have to produce an FM from if you have to produce the PM signal, phase modulated signal, from FM signal, then you have the following schematic. If you look down at the following schematic, the only difference is it looks very similar to what we have in the basic structure of FM transmitter. The only difference is that we are having a differentiator. Okay, and why this differentiator is over here. You see, starting from the microphone signal, you have an audio signal. Okay, and the output V1T. V1T is again it's RC dV by dt. This is the derivative of the audio signal produced by the microphone, so dV by dt. Okay, and you see that this thing comes over here. This thing is over here. You're looking at this is the expression. So if the voltage control oscillator has the voltage controlling the oscillation of that oscillator is V1T, and that is RC dVA by dt, then you don't have omega A in the denominator. Okay, you don't have omega A. And why is that? Because okay, you look at this expression. This omega t is omega naught k oscillator RC dVA by dt, and since the phase is the integration of omega, then that can be written as such. Okay, so this differential, this vanishes, and what you are left with is RC A sine omega AT. Okay, and since this is the integration, you cut out the derivative part. So that's your phase expression that you are left with. Okay, and which is equal to omega CT plus K oscillator A times plus K oscillator A times omega AT. So that in the denominator there is no omega A. There is no omega A. So that's the only difference in the phase and in the frequency modulated waveforms. And if you can make RC equal to 1, you don't see RC in the last expression. You don't see any RC with K over here. Well, that can be done. So if you can set RC equal to 1. So what happens over here is that you are directly varying the phase. This is the phase, and this phase is being varied in proportional to the audio signal. In this case, the audio signal is a single tone. So that's the phase of the phase modulated signal, and you need a differentiator. So just to avoid omega A over here, because you need a differential over here which cancels with the integration operator. Okay. So in a sense, the phase modulated and frequency modulated waveforms, they don't look much different from one another. Both are angle modulated schemes. This is the possible receiver for PM wave. For a possible receiver for PM would be the FM receiver, which is shown below. Okay. So this is a basic FM receiver. We can have a receiver for PM, which can be constructed from this receiver. So let's see in detail how this filter helps in getting out the or obtaining the original modulating signal. So a possible A receiver for PM would be an FM receiver, okay, with an integrator after the diode detector over here to undo the differentiation done in FM transmitter. So because in PM you had a differentiator in the receiver side. If you have an integrator, it will undo the effect of differentiator. So let's try to understand this schematic. What happens is that once you have the FM signal, which is, let's say, this is your carrier frequency FC, and it has excursions both at the positive and negative side. So you have sidebands like this. Okay, you have sidebands like this, or whatever. Okay, different stunts. You have a filter. You have a filter over here. And if you look at the circuit topology of the filter, it's a bandpass filter. Why it's a bandpass filter? It consists of series LC circuit before a parallel LC section, and if you are setting the resonance frequency 1/100 LC of this filter as the center frequency of a band pass filter, let's call this F0, then at this F0, and if this frequency is my F0, if this frequency is the center frequency of the band pass filter, you see it makes sense that at the center frequency this series LC will be a short circuit. Okay, series LC will be a short circuit, and at resonance this will be an open circuit. So basically at F0 you will have the signal feed through this filter with the minimum possible attenuation. Okay, so but when you are deviating from F0, the center frequency, then again the impedance takes over of the series arm and the parallel arms of the filter, and the frequencies start to suffer the attenuation loss. Okay, so on either side of F0, the impedance increases of the series inductor, and you have the decreasing or attenuating gain response of the filter. So it's a band pass filter. This filter is a band pass filter. Okay, so let me say that is also a band pass filter. You see at the start we have a limiting amplifier. Well, why we have a limiting amplifier over here is that you decrease the amplitude. Okay, because we know that the information is, for example, in FM, the information lies in the instantaneous frequencies. For example, over here the frequency is low, then the frequency is high. But if this amplitude is this amplitude has to stay constant. Okay, this amplitude has to stay constant. But if there is some deviation from this amplitude like this or whatever, if you're looking at it, can be clipped over. Okay, you don't need this. We know that the information is not in the amplitude; it is in the frequencies only. So this limiting amplifier, actually what it does is written over here. Filter is a refinement to eliminate the amplitude noise, as well to make the audio volume independent of the signal strength. So actually it helps in increasing or refining the SNR. Okay, now let me redraw this filter response over here. It's a band pass filter. Okay, it's a band pass filter, certain frequency, let's say center frequency F0. And then we have our carrier, which is located at the edge. In this figure, I think I've drawn many sidebands over here. Okay, so it's located at the edge. So let's see how it converts this signal into a varying amplitude signal. You see, because the rest of the part, what we have discussed before, is a diode detector followed by a low pass filter. Well, that's your envelope detector, right? So that's the same as the envelope detector for AM modulation scheme. So what is happening is that around FC, if we do not go any further from FC, you have excursions or deviations from FC as you have in FM. So for example, for a frequency that is lower than FC or much lower than FC, for example, if you have a maximum deviation from FC, that means let's call this as FC minus F max. That's the maximum deviation. Okay, that's the maximum that you can go. That means the amplitude is high over here. Okay, the amplitude is high. This results in, let's call this A max. Okay, and a frequency that is close to the carrier. Let's call this A minimum. Okay, that's how the response is. That's the slope. That's how this slope converts the FM signal actually into an AM signal. Okay, so you see that at each frequency deviation from the FC, you have a different amplitude. This amplitude is different. This amplitude is different. So each frequency is getting a different gain from the slope of the filter. Okay, so from the slope of the filter, you won't have a constant amplitude. You will convert this, for example, over here. This is the maximum deviation. If this is the highest frequency, you will have the maximum deviation. So a maximum signal comes over here. Then a minimum signal comes. A maximum signal comes here. So that's how you're going to convert an FM into an AM basically over here. And then this diode, after this diode, you will have only a positive envelope like this. Okay, so the deviations will be only of the positive half cycles like this. Okay, so what you have actually before the diode is you have this AM envelope. You have an amplitude modulated envelope, and then this is a low pass filter. So what happens is that again you're going to charge up your capacitor. Your capacitor is charged, then it discharges, then charges, discharges, charges. It charges in the positive half cycle. In the positive half cycles when the diode is PN junction is forward biased. The negative half cycle when the diode is reverse biased, the capacitor discharges across the resistor. Okay, so that's how you're going to detect this envelope. So you are detecting this envelope, and if this is the envelope, well, you have something like this. So it's not very nice, but anyways, you get the idea. So actually that's what we have discussed before as well. Well, basically you will have some detection like this. Okay, so yeah, like this. So this is your low frequency modulating signal. So actually FM, this was a modulating signal. If this was a modulating signal, the envelope is detected as such, and that's how you convert actually in this scheme an FM to an AM signal, and then you detect the envelope. Okay, so this part is the envelope detector. This part is your envelope detector. So this is again the coupling capacitor to remove any DC. So you remove the DC level, and then you're going to listen to the piece of music or whatever the audio signal is, speech signal or whatever. So as the instantaneous frequency deviates from the carrier, it's written over here, the variation of the amplitudes with respect to the frequency is recorded. So what you are recording over here, okay, after the filter, you are recording the differences in the amplitude. We are recording different amplitudes with respect to different frequencies. More deviation, more the frequency is. Okay, and that's what has actually happened in the FM signal. And low the deviation is, well, then there is a low amplitude, of course. So that's how you convert an FM to AM. So that's your FM receiver, but yeah, it converts it to AM signal. And then you have envelope detection. Okay, so then you are detecting in an envelope, and that's your envelope over here. So that's your envelope detection. And that's how you retrieve your information from the audio signal. So rest of the receiver is an AM receiver. Okay.